All right, so far we've talked about ionic bonding in chapter 5. We've talked about ion dipole intermolecular forces. We talked about dipole-dipole intermolecular forces, including hydrogen bonds. Now what? Now we're going to talk about dipole-induced dipole intermolecular forces. These are attractive these are attractive forces between a polar and a nonpolar molecule. So one of them's polar, the other one's not. It's not an ion either. It's just a polar molecule and a boring nonpolar covalent molecule. So nonpolar molecules don't have a permanent dipole. So they don't have that net dipole that I told you about when we were talking about the polarity of a molecule. These don't have permanent dipoles, but they can exhibit something called an instantaneous dipole or an induced dipole. So what happens then is the negative end of a water molecule can interact with an O2 oxygen gas molecule. So water here is polar, it's got a dipole, and if it interacts with little old oxygen gas with no dipole, then the partial negative charge on oxygen is going in the water, the partial negative charge on the oxygen atom in the water molecule distorts the electron cloud of this here oxygen gas molecule, O2 molecule, and induces a dipole on this molecule. So this negative end of water gets close to the oxygen molecule, and that causes the electrons that are in this O2 bond to kind of shift away. They're being repelled by the electrons that are localized on the oxygen of the water. So they're electrons, it's electron dense. We've got a partial negative charge on our oxygen atom in the water molecule. And those electrons are repelling the electrons that are in this here bond between the O2s, or between the oxygen atoms in O2 molecule. So the electrons in that bond are trying to get away from the other electrons. So they move to the other oxygen, closer to the other oxygen atom, making this one partially positive for a hot second, which is why we call it an instantaneous dipole. It's not going to last very long, but it is noticeable. And it's good to note that if we did it the other way and we had an oxygen molecule over here and the positive end, the hydrogen, was interacting, then we would cause the electrons in the bond to want to move towards that positive charge, and this would be the partial negative, and this would be the partial positive in our temporary dipole. So it can go either way. This figure just showed it with the oxygen of the water molecule interacting with the O2 molecule, but it can go either way. All right, because induced dipoles are temporary, when the H2O and O2 molecules separate, the oxygen gas electron cloud is no longer distorted, and we go back to having no dipole and our electrons equally shared between the two oxygen atoms. All right, so we get rid of it when the interaction is no longer happening. It's a fleeting intermolecular force. Because of that, they're generally weaker than dipole-dipole forces, but this depends on the magnitude of the induced dipole. So we have a term for this. How much the electron cloud in a molecule can be distorted is called its polarizability. So your book mentions this term, maybe not in quite this way, but they say that certain molecules are more polarizable than others based on their electron clouds, based on their or arrangement of electrons in the molecule. So what's this polarizability thing? How do we predict it? How do we know which is gonna what molecules are more polarizable than others. Polarizability increases with the number of electrons in a molecule. Therefore, we have increasing molar mass or size. So we're going to relate mass and size here, which is not necessarily always true, but that's what we're going to say for polarizability, is that increasing molar mass and or increasing molecular size results in higher polarizability, more polarizable molecules. All right, so your book didn't really talk about those induced dipole intermolecular forces, but I think those were important to mention to get here. So induced dipole, intermolecular forces occur between two nonpolar molecules. So now we have two boring nonpolar molecules, just regular old covalently bounded molecules interacting with each other. These types of molecules can still induce temporary dipoles in each other, depending on how they interact. So if we look at iodine gas, we've got two iodine gas molecules interacting with each other. So two I2 molecules interacting with each other. The electron clouds repel each other and temporary dipoles form. So if these little molecules get too close to each other, they distort each other's electron clouds, forming these induced dipoles. So it doesn't really matter which way is which, but we end up with partial positive and partial negative ends together, because that's more favorable than having like charges. And we end up with an induced dipole in both of our molecules. These induced dipole intermolecular forces are also called London dispersion forces, or sometimes just dispersion forces. So dispersion forces are generally weak, but they can be stronger than dipole-dipole forces. So one of the first ones we talked about, dipole-dipole forces that are usually pretty strong because we got polar molecules interacting. But these dispersion forces can be stronger than those forces if we have highly polarizable molecules. So let's talk about that. Dispersion forces are important in all liquids, even polar ones, because the electron cloud of any molecule can be distorted by partial charges in surrounding molecules. So this is important to note, that we have dispersion intermolecular forces in every molecule ever. Every interaction of atoms and molecules in a pure substance includes dispersion forces, always. So if I ever ask you, what intermolecular forces are there in this system, you should always answer dispersion. These other ones might also exist, but always dispersion. All right, anywho, down here, we see the dispersion forces and their impact on boiling point of these halogen diatomic molecules. So fluorine has a small molar mass, chlorine's is bigger, bromine's is bigger, and iodine's is the biggest. So I2 molecule here is the biggest. So we're increasing in molar mass, so we're increasing in size. So we're getting more polarizable. Remember, when we increase in molar mass or molecular size, we're increasing the polarizability. So when we get more polarizable, that makes the dispersion forces stronger. So we get stronger dispersion forces, and like with the dipole-dipole forces, we have stronger forces. That means that we need to heat it up more to get it into the gas form. So in fact, the boiling point of fluorine is so low that it's usually a gas at room temperature, or always a gas at room temperature, unless you do something fancy to it, I guess. Chlorine is the same. It's got a pretty low boiling point, so it's a gas at room temperature. Bromine is a moderate boiling point, so room temperature is about 25. So the boiling point's above 25, so it's usually a liquid at room temperature. And if we keep going, iodine has the strongest dispersion forces holding it together. So a sample of iodine molecules is found at room temperature as solid because these molecules are held together very tightly. We got a dense, condensed phase, which is a solid. Alrighty, let's investigate this a little bit more. These are just more examples of the diatomic elements with weak dispersion forces that are gases at room temperature. And just looking at polarizability again and boiling point. So these are all nonpolar compounds. So again, we got chlorine and bromine on here. Sorry, my computer just yelled at me. We've got chlorine and bromine down there, but we've got a few other ones, some tiny ones like helium, neon, nitrogen gas, oxygen gas, argon. So again, we are increasing in molar mass as we go down the table, and we are likewise increasing in boiling point because we are getting more polarizable molecules. We can see this in hydrocarbons as well. So hydrocarbons are nonpolar. These have a similar structure. These are basically carbon chains where we got 1 carbon, 2 carbons, 3 carbons, and they've got hydrogens coming off of them, 4 carbons, so on and so forth down this table till we get to C18H38. So we get to 18 carbon molecules in a chain with hydrogens coming off the sides. So we're going down here, we're getting bigger in molar mass and the length of this carbon chain. So now we can really see the molecular size. The molecular size or the length of the carbon chain is increasing. So is the molar mass. But now we can see the size a little bit better than we did before. So as that increases, as we go down the table, so does our boiling point. So this is all based on dispersion forces, polarizability, because we don't have any polar molecules here. The diatomic gases on the previous slide and the hydrocarbons here are all nonpolar molecules. So these are just dispersion forces, nothing else. No hydrogen bonding, no dipole-dipole forces, nothing, just dispersion forces. All right, let's take a step back and think about water some more. So, and hydrogen bonding. So life as we know it wouldn't exist without water. We would die without water. That's why we're looking for other planets and moons and things that have liquid water on them. So without hydrogen bonding, most of the water on our planet would be found as water vapor. So hydrogen bonding is responsible for us having liquid water on Earth. Because if we just looked at the polarizability trend, the dispersion forces in water and its related molecules, then polarizability tells us that water would have a low boiling point. But thank goodness for hydrogen bonding because it has a high boiling point and we get to live with liquid water on our planet. So this is just showing as we go down the group. So this is group 16. We've got oxygen, sulfur, selenium, and tellurium. As we go down this group 16, we're getting bigger. So the molar mass of these atoms is getting bigger. So we would think that the boiling point would be getting bigger. It'd be like 1, 2, 3, 4, which is what we see for these three. We see that as the molar mass goes up, the boiling point gets higher. But if that was the case, then we would have water actually down here somewhere, which would be bad for life as we know it. So thank goodness for hydrogen bonding. And this just follows up on that. If the trend in boiling points based on polarizability is extended to H2O, so decreasing molar mass as we go backwards on that graph, then boiling point is expected to decrease and be low because of polarizability. But we know that water has a boiling point of 100 degrees Celsius because of the extensive hydrogen bonding in water. Hydrogen bonds in water influence many of its physical properties. Its high boiling point being one of them, but also its high surface tension. If you've ever seen those little bugs that like walk on water, that's because water has a really high surface tension. And its high heat capacity. So heat capacity is how much we have to heat it up to change its temperature. So we'll learn a lot about that in chapter 10. Just to follow up here, ethanol and dimethyl ether have the same molecular formula, which means they are called isomers. We talked about structural isomers a little bit in 7.3 or 7.2, sorry, when we were talking about trans and cis isomers. So these are also isomers. They've got the same molecular formula, 2 carbons, 6 hydrogens, and an oxygen, but they have very different boiling points. Dimethyl ether has a super low boiling point. Ethanol has a high boiling point. And that's because we have hydrogen bonding. We have an OH bond, so we have hydrogen bonding in ethanol, and we don't in dimethyl ether. It's only got an oxygen. It's got oxygen-carbon bonds, which means it can't hydrogen bond with other molecules of itself. It can only have these dipole-dipole forces instead of a beautiful, strong hydrogen bond. So ethanol has hydrogen bonding because it's got an OH bond, so it has a high boiling point because hydrogen bonds are stronger than dipole-dipole forces, other dipole-dipole forces, I should say, in molecules of the same size. Okay, so there's a lot of different things to keep in mind when we compare intermolecular forces. So, because intermolecular force strength depends on the magnitude of the partial charges, we predict that polar molecules have stronger intermolecular forces than comparably sized, this is the key word, comparably sized nonpolar molecules, which we see in this table is true. In each pair of molecules with a similar molar mass, the polar compound has the higher boiling point. So N2 and CO, they both have a molar mass of 28, but carbon dioxide has a slightly higher, carbon monoxide has a slightly higher boiling point. SiH4 versus PH3, they're about the same, 30-ish grams per mole, molar mass, but we got a higher boiling point. So we keep going, we see that same trend. So the polar ones have higher boiling points when we're comparing similar sizes. And here's just a little summary for you of intermolecular forces and relative strengths. So dispersion, once again, is in all types of atoms and molecules, all of them. If I ever ask you what kind of intermolecular forces something has, dispersion should always be one of your answers, always. Dipole-dipole, like in HCl, hydrogen bonding, anything with OH, NH, or FH bonds, and ion dipole forces, like an ion dissolved in water. So you can see the relative sizes here. Ion dipole is stronger than dipole-dipole. Hydrogen bond are the strongest of dipole-dipole bonds. So they can be, they're usually still kind of less than ion dipole, but they could be more. And then dispersion forces are generally the weakest, although I have a little note down here at the bottom about dispersion forces and dipole-dipole bonds, or intermolecular forces, I shouldn't say bonds. So dispersion is between all types of molecules, so including really, really big ones, and that means it's on average stronger than less or stronger than simple dipole-dipole bonds, which usually occur in smaller, less polarizable molecules. So it's all about polarizability and the types of molecules we are examining the forces in. So this is just a general overview, not anything that needs to be memorized or anything. All right, let's finish up by talking about 7.4 real quick. So there's no homework on 7.4, valence bond theory, but it is important to know. It'll help us explain some things in 7.5 and 6, I think. So just like how Lewis structures didn't tell us the whole story of the geometry of molecules, like how Lewis structures made water look like it was, you know, linear, or sorry, if we put one of those down here, it could be linear. The Lewis structure didn't tell us the whole story. Just like that, Lewis structures and the VSEPR model don't tell us the whole story of covalent bonding. So we need to consider atomic orbitals. Remember back to chapter 3 and 4 when we started talking about quantum numbers and electron configurations. We need to consider that stuff again because that is very important for bonding as well. For example, hydrogen and fluorine gases have very similar bonds if we just look at their Lewis structures. It's just, you know, a linear bond. Not really telling us a whole lot about what's going on, but they have very different bond lengths and very different bond energies. So why is that? So if we consider this valence bond theory says that we have an overlap of these orbitals. So this is a hydrogen, this is a 1s orbital, this is another 1s orbital. So hydrogen has one unpaired electron. It only has that one electron to begin with. But when these two hydrogen atoms come together, their single unpaired electron can be shared with the other one, and we end up having two electrons. We end up having a pair of electrons in our 1s orbital. So each hydrogen is thinking that it has a 1s2 configuration. It thinks that it owns both electrons. So we have an overlap of our orbitals, which results in a bond. Fluorine and fluorine, on the other hand, so if we remember what fluorine's electron configuration was, it was 2 helium, 2s2, 2p5. So you should refresh your memory on that for sure. So 2p5 means that we have, let me draw this again, in this format. So we got two groups of pairs of electrons and one by itself because we only have 5. We can't fill those p orbitals with only 5. So we got this one unpaired electron in a p orbital. P orbitals look like this. So these two, the darker blue ones, are the ones that are filled. And this lighter blue one here in the x-axis, that one is the p orbital that is not completely filled. That's the p orbital that needs another electron. So both fluorine atoms look like that. So they both have that single unpaired electron, and if their orbitals, their atomic orbitals overlap, then we end up with a bond. And you can see, or at least I hope you can see, that because of the size of the p orbitals, when they overlap, this bond length is longer than the bond length in the hydrogen molecule. And that's how valence bond theory explains bond length and bond energy a little bit. And these are kind of only in overlapping like on a little end, so it's easier to break apart. Whereas hydrogen is overlapping on like a big scale. It's like a nice Venn diagram. So it's harder to break apart. Cool. So here's our definition of valence bond theory. According to valence bond theory, atoms share electrons when an atomic orbital on one atom overlaps with an atomic orbital on the other. It doesn't have to be the same kind of orbital. As we see down here, we have an s orbital on hydrogen overlapping with the p orbital on fluorine. So it doesn't have to be the same kind, just has to overlap with an atomic orbital of the other atom. And each of these atomic orbitals must contain a single unpaired electron that we want to pair up with the other single unpaired electron in the other atomic orbital it's overlapping with. And furthermore, these two electrons that are going to be in this bond, so these two electrons that are going to be in overlapping atomic orbitals, must have opposite spins. And we can see here, our 1s orbital on hydrogen is going to bond here with the 2p orbital on fluorine. So we get an overlap of those atomic orbitals, which is what forms our bond. So it's an overlap, and the electrons in there have opposite spins. So we've got our 1s electron from hydrogen, which is coming in, and it's going to have this spin, and it's going to jump in here, and we're going to have filled orbitals for fluorine and a filled orbital for hydrogen as well, because this little guy is going to sort of also be filling the 1s orbital for hydrogen. So we're going to have quid pro quo, a sharing of electrons filling both types of orbitals, so that each atom thinks that they have all the electrons they want. All right, so we're going back to a graph that we've seen before. This is a slightly different version that's actually from this book and not my old book. So we didn't get this far before, I guess, but I kept using this figure ahead of schedule, I guess. So valence bond theory explains why covalent bonds form, because we have a minimization of energy. So this is potential energy, and this right here is a minimum. So it's a minimization of energy. The potential energy of the overlapping orbitals is lower than the combined energy of the individual atomic orbitals. So these two potential energies of these atomic orbitals added up is more than the potential energy of the overlapping orbitals when they get to just the right distance apart, this 74 picometers. And that minimization of energy, so what that means is when the bond forms, we have a release of 436 kilojoules of energy. So when we break bonds, we have to supply energy. Energy is absorbed to break a bond. When we form a bond, energy is released. So it's just the opposite. And finally, valence bond theory also explains some discrepancies we see in bond angles found experimentally compared with VSEPR theory. So VSEPR theory would tell us, oops, VSEPR, there we go, I remember how to spell VSEPR. So VSEPR theory would tell us that H2S would look basically the same as H2O, would look like water with a sulfur instead of an oxygen. So this would be a tetrahedral electron geometry and a bent molecular geometry. You should know that already. So this bent geometry would be somewhere around 109.5, a little bit less. So water, it's like 104.5. So it's a little bit less than 109.5, but still pretty close. But experimentally, we find out that it's this, and that doesn't make any sense based on the VSEPR theory. But it does make sense based on valence bond theory. So valence bond theory, again, comes from these orbitals overlapping. So we have two singly occupied p orbitals on sulfur atom. So sulfur has this configuration here. Ne 3s2, 3p4. So it's got two unpaired electrons. So that means it has two singly occupied p orbitals. So those electrons spread out so that they're in different p orbitals. So those are the light blue p orbitals shown here, one in the x direction, one in the z direction, I guess. So we have two of those for hydrogens to bond to. So those, we have an overlap of our 1s hydrogen orbital and our 3p sulfur orbital. And then we have another one on the other singly occupied p orbital. And because the p orbitals are perpendicular to each other, that means that these bonds, so the sulfur hydrogen bond, is going to be about 92 degrees based on valence bond theory and not VSEPR theory. So there's a lot to keep in mind, guys, and I know that it's a lot of information and sometimes it's conflicting information, but it all adds up into the complete story of bonding. So we need to consider both VSEPR theory for some things. It helps us explain the shape of water, for example, but sometimes we need other theories to explain experimental results that don't make sense. So we have several different theories all combined to give us the whole story. And this is one of the new theories that we discussed after talking about Lewis structures and VSEPR theory. There's still more to come. Sorry. I'll see you tomorrow.